Oh, sorry.
He said some, yeah, he said something.
Sorry, I was talking.
Oh. That he just
Sometime this weekend. I got to catch up. This week's been...
No, of course. I was just wondering when the
I keep checking every day. I've been checking every day.
Yeah, I know. I understand that. I try to do my best on this too, but this, my bike ride and everything sort of got me where now I'm like behind.
Are you curving?
Probably not, because I gave every answer on the test. So, I mean, I'm not going to really... Because there's going to be plenty of people getting 5960s, so no, there's not going to be a curve on that. But hopefully you guys did well. But, you know, it's pretty... if you can do it. All right, so, again, the good news... The good news is that Calamar's taking their test on Monday. Ooh, that'd be bad. You get an extra week just because I love you guys. And again, reminding you, we're not doing chapter 24, so I'm actually going to go ahead and quickly kind of do these major things that we did last time in chapter 15, and then add the last couple things. And, you know, maybe that's even all. Okay, I'll see. Chapter 16 is literally 30, 40 minutes. Okay, it's a real basic thing. It's not going to be like chapter 15 at all. And so, you know, probably I'll just do that Monday, and then the rest of Monday and all of Wednesday, including lab time, it's review. But the key is those extra questions. Okay, so the sooner, especially the sooner you can get this, most of it involves chapter 15, and really this baroreceptor / epinephrine thing that I'm going to even put way up. That's going to be the real key to understanding like stuff which we haven't even covered quite, you know, in class, right? And doing those extra questions, looking at what calcium channels or blockers will do on all the extra potentials and things that you just learned. And so that's what I'm going to want you. We're going to really want to work on next week, and you really want to come prepared. You don't want to just not do it at all, and then Wednesday, you know, what are the answers? You can't do that, I guess. But I mean, this gives you the opportunity to know this material really well. And that's going to be the goal. So I'll keep this up for right now. Obviously, that's not going to be on the test, but we'll go ahead and put this thing up. You know, we'll put the cartoon up.
That's the name.
This is, I mean, again, I'm making a real quick cartoon. There's my heart. Here's blood pressure. Here's the arterials with the resistance. The other thing, too, is that remember, those are my veins. Remember, on the regular study questions, there's some questions on comparisons of the different muscle types, and a couple questions, slow wave potentials. What are those, Mike? Okay, the end of chapter 12 of the actual book that we did on skeletal muscle, that has a section on smooth muscle, and it has like a table that compares the three types. That's up to you to sort of look at. I got copies in the lab if you don't have the book. Look at that and see if you can get the basic points of what the main differences are. And so don't forget to do that, because I have some questions on the test for that as well. But we've got time. So we've got this guy up here, okay, to help us out. And the real idea is, for the arterials, we have this idea of constriction dilation. Overall, that is creating what? What do we call this side of it? Peripheral resistance. PR, okay. Now, on this side of the blood pressure coin, we have the heart pumping out blood. And pumping out blood is what? Cardiac output. Cardiac output equals what? Times stroke volume. Stroke volume. We have the detailed parts of it. Stroke volume equals what two things?
ESV and ISV.
Well, ISV. Wait a minute. Let's calm down. EDV, which is what we put in, minus, which is what is left after systole. Okay? And again, veins are important because basically veins are under very low pressure, and so we care about something called what? Venous return. How much of that are we getting back? Okay? By the way, just out of curiosity, we have these veins and these arterioles that are responding to the sympathetic system, constricting and dilating, right? Constricting and dilating. That sounds like a muscle, right? What kind of muscles are they? Smooth muscles. That's where if I haven't made that clear, because I just talk about it, that's where smooth muscles are coming into the picture here. They're involved in the vasoconstriction, vasodilation of all these vessels. That is the muscle layer. That is what's actually doing it. That's why when you look at how smooth muscles work, well, and compare them, that's what you're sort of trying to follow here. There's smooth muscles in our digestive tract, blah, 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 other places too. We're just not going to concentrate on them in this section. Okay, so we had that, right? Okay, so let's go ahead and we'll do this over here. We're going to do the baroreceptor response. We're going to do the exact same one you're going to do all on the test for 14 points and use for 30 more points. And when you look at those extra questions, you're going to see how to reason it looking right at your last page. You're going to keep going back. Yes, there's the answer to that multiple choice. There it is. Okay, that's the key. That's why we do this. That's why I tell you it is. So we'll do, again, low blood pressure. We gave one example. It doesn't have to be that example. One specific example of low blood pressure would be the idea of orthostatic hypotension, in which you're sort of laying down. Okay, I was like laying in my car trying to take a nap for 5 minutes, and I jumped up and I felt lightheaded, and I said, my baroreceptor response is going to take over. So orthostatic hypotension. The key is, whatever does it, low blood pressure, and you're thinking something in our body is going to react, sense this, and they are the baroreceptors. I know that. It's like, what do you want, Mike? Now we're there, right? Baroreceptors, and where are they located? Because I'm asking all, this is the essay question. Aorta and carotid. They're responding to low blood pressure. All these, I don't know if I care on the test as much, but you're going to mess yourself up if you don't. All these write the goal, okay? The goal will be to raise blood pressure. Because you don't want to be like getting the wrong thing down here and you're like, wait a minute, I forgot the goal. Goal is to raise blood pressure. And to do that, again, we sort of help us out here right now with this. Remember, we're sending information up to the brain. The brain's going to send a response. The response is to the autonomic nervous system. So the next thing you write is it's going to increase one and decrease the other. Okay, if our goal is to raise blood pressure, decrease parent. Okay. Then you like, okay, good, I'm starting off good. I'm going to take a drink of my vitamin water or whatever drink that is. Because I got plenty of time on the test, so I'm not going to mess up. Then we remember, I'm going to want 5 columns based upon this. And I'm going to want to know the neurotransmitters, because that's going to help us on when we do alpha blockers and beta blockers. And so, let's kind of get this here. I would definitely prefer, if possible, to do it like we're doing it, and to including the abbreviations and stuff, because when I'm grading 100 of these, it just helps me out versus reading sentences or trying to decipher if you kind of get something in the middle there. And I do, again, I'm not a very anal person, as you can kind of tell here, but I'm very sort of specific on the order of things that I want, because I want you to see the flow of it. If you miss one, that's like, like ESV, you lost a half a point, so don't freak out, but it's going to really help you understand this. So we have 5 things. And we're going to write the neurotransmitter, and we're going to write the receptor. And again, I start the same way just to keep consistent. We're going to decrease para where? Yeah. You don't even need this anymore because you guys are good. To the SA node. I don't care about numbering, I just care about order. Neurotransmitter. ACH, meaning acetylcholine. Acetylcholine will bind to what receptors in the SA nodes? Muscarinic. Okay? Now, when we decrease the amount of parasympathetic, the amount of acetylcholine going on the SA node, its direct effect is what? And what's it going to do to heart rate? Because we're getting rid of a negative. If you increase heart rate, you cardiac output. If you increase cardiac output, you increase. Okay, are we done with that column? Okay, don't skip to the end. Okay, get all of them. Increase heart rate, therefore increase cardiac output, therefore increase blood pressure, and we're done with the parasympathetic's role in this thing. Okay, everything else is sympathetic. For sympathetic, what is the neurotransmitter in every case? Norepinephrine. Any is fine. You don't have to make a legend. Okay? I know you know this stuff. Okay? You can. I don't care. I mean, some people you got time to make a legend, but I'm not. You do not know what norepi means. And what does that arrow mean? Okay? It's because we're all on the same page here. So we're gonna systematically go through this. We're gonna remind ourselves we're raising sympathetic to the SA node. What is the receptor on the SA node for an RFE? And so make sure now we know why I was sort of emphasizing before beta 1, because there are beta 2s on other things. But beta 1s, most beta blockers, that's where they're working. They're not on beta 2s. They're on beta 1s. Okay? And so we have that. So if we increase sympathetic to the beta 1 receptors, norepi, what happens? If we increase heart rate, if we increase cardiac output, are we done with that column? Yes. They should match. And they do. And we're done now with heart rate part of this. That means the next two probably going to involve stroke volume. And yes, you're right, they are. So we're going to stay on the heart, and we're going to basically increase sympathetic to the ventricular muscle. What are the receptors for an RFE on the ventricular muscle? Okay, beta blockers work on both of these. Okay, norepinephrine's binding to the SA node and the ventricular muscle.
Beta 2?
Beta 1. I don't know. I was like, okay, so now we're not quite ready for the equation because we have to say, well, it's doing something to the muscle. Okay, so if you add sympathetic stimulation to the ventricular muscle, it's going to do what to that muscle? Action. Increase contractile force, force contraction, anything like that. So, I'll put increased ventricular force for this, vent force. But I don't, if you got any of those, we got that. Okay, now, what's the next thing you're going to put? If you increase ventricular force.
You decrease
Okay, remember, ventricular force had to do with squeezing, how much was left. Okay, we're squeezing harder, that less is left. So we're decreasing ESV. The end systolic volume. What is left after we contract? What is left after systole? Okay, what comes next logically? Increase stroke volume. Because stroke volume is what we eject. If we squeeze it harder, we're ejecting more. If you increase stroke volume, what follows? And blood pressure. Don't throw heart rate in or you lose a half a point because we're done with heart rate there. This is affecting independently. Increase stroke volume, increase cardiac output, 6 is increase blood pressure, and we're done. Okay? So, we do the next one. The next two, we're done with the heart here. We're on the veins and we're on the arterioles here. So the veins we're still going to be involved in here. So we're increasing sympathetic stimulation of the veins, which are going to affect the smooth muscles on them. Now, as far as an RFE on these, what receptors are they binding to on the veins? Alpha. Beta blockers don't work on this. Alpha blockers do. Okay, but anyway, norepinephrine's we're increasing it. That's one. So if we increase sympathetic stimulation in the veins, it's going to cause what? Vasoconstriction. Okay, that's what increased sympathetic will do. We'll put vasoconstriction. And if you increase vasoconstriction, you can kind of look over here. What is that going to do? Increase venous return. And I jump up and down to venous return. It's very important because there's a big deal here. It's sort of something that might not be obvious before we start doing this chapter. We know we have veins and and capillaries and arteries and capillaries and veins, completely different vessels. Okay, we have these arteries and arterioles, especially the arteries, which are very elastic. Blood comes in, they have high elasticity, they come back to where they were, that propels blood. Okay, that's their job. Okay, if you look, and their structure sort of matches. If you look at veins, their job is basically, they're not very elastic. As blood is coming in here, we have that picture, they're very compliant. They're like a plastic bag, not a balloon. Blood comes in, and they sort of just accommodate the blood. We don't just quickly send it back to the heart because we don't need all that blood pressure or cardiac output if we're just sort of sitting here. We want that as reserve. If we need to now run away from that bear, okay, then we're going to get increased venous return, get it in this compartment, and boom, blood pressure and distribution to all the tissues can increase. So you really want to see the difference between these vessels and these compartments. So now we need it, okay? We don't have enough of this blood pressure, so we're going to say, okay, veins, we need some of the blood. So by actually having the sympathetic stimulation, again, I used to just talk, well, it squeezes them and there's only one way to go. It's just simply not really accurate. The idea is it lowers its compliance. Compliance is the ability just to expand like a plastic bag and stay there. And so by constricting it, when the blood comes now, it's going to more rapidly just propel to the heart. It's almost like, if you had a plastic bag, it would kind of just fill up. If you stretch that plastic bag, it will go through there faster, right? It won't just, because it won't just kind of, expand. That's what this is really doing. So increasing venous return, I didn't mean to ruin the rhythm there, but very important concept. But we've increased venous return now. What follows next? We increase what we put in, EDV. What will follow from that? Increased stroke volume. Because, again, a slight diversion, we have this idea of why. This is the Frank-Starling Law, that if you return more blood to the heart, it will pump that out, because the cardiac muscle cells relied upon extracellular calcium, right? If you look at the difference between that and skeletal. So as you stretch these muscles, which you are when you put more blood in, more calcium comes in, and more calcium in cardiac cells means what to us? More force of contraction. So it's literally, basically taking what got in, because it got stretched, it basically, more calcium comes in, it will pump that out. You put even more blood in, more calcium, it pumps it out. So it's good. If we can return more here, it doesn't just accumulate and stay in our ventricles. That would sort of suck, or in our lungs, right? It's basically, if we're okay, it's going to basically be pumped out here. We put more in, it automatically will pump it out. That's just the nature of these cardiac muscles. Pretty cool. So, you got it right. If you increase stroke volume, and so I know I ruined the rhythm, but you can do the rhythm yourself. I just wanted to emphasize it. So that's that. That's the longest one. And we're done now with this side. Can we take another drink? Look at the time. We still got 2.5 hours for the test. We're like, okay, we're over here now to the last one. We're increasing sympathetic to these arterioles. What are the receptors? Alpha. 1. What's this going to accomplish by increasing sympathetic to the arterioles? Vasoconstriction again. And in this case, vasoconstriction, increasing that resistance, and therefore, boom. So again, that's your essay. There it is, 14 points. Okay, you do it right away. That's what I'm going to want. Perfect, having it with the arrows, etc., like that, and just naming everything. But especially as you start going on those extra questions, which we won't go totally today, you're going to see, because remember the multiple choice questions. You love my multiple choice questions, right? The key with this is, okay, and you guys are the survivors, and some of you are doing really well, some are like, I've got to get that extra step. The key with this is, it's like all the multiple choice questions are based upon these basic things that you've been practicing. So if you write these basic things on your test and figure out the answer is there, and you just have to find it in that multiple choice, okay, to eliminate things. And so luckily for this one, there's a lot of them that, the answers are here, okay? And when you do those extra questions, you'll see what I mean. You'll literally, and I did this today with my Palomar class because again, their test is Monday. That's why next week we want to do that. You start going back to this, and you're going to start to see how many answers are here. Okay? And the same thing that I was already talking to one student at office hours, you're going to review the action potential of the contractile cells, right? What happens, da-da-da-da-da. The action potential of the SA node, the pacemaker, da-da-da-da-da. And, and how muscle cells contract, calcium in, calcium out. And then on the extra questions, I talk about what happens with a calcium blocker to each of those. And so, and then I'll have specific multiple choice, but, if you just draw, okay, in fact, let's look at that a second. That looks like an action potential to me. What is that an action potential of? Pacemaker cells, like the SA node, right? Okay, pacemaker cells. So some of us might have reviewed this, but why not? Let's just kind of do this. Now we have a week and a half to keep kind of going back and forth. Don't wait to the end on this. Okay? So these are the pacemaker cells like the SA node. And what do they control, by the way, just in general? Heart rate. Right? Heart rate. 1, 2, 3. What's causing this slow depolarization of threshold? Buddy channels. Just to remind us. So funny channels are what? Leak channels. And they leak which ions? And sodium's going to leak. Potassium leaks out just like before. Who wins this battle? Sodium's leaking in. Okay? And you can review that. What's 2? Depolarization caused by what? Calcium. Okay? That's why you're going to review later, but it's just I just want to keep doing it. This case, calcium's coming in. Okay? Unlike the other cases. Calcium's causing depolarization. What always causes repolarization? Potassium going out. Okay? So, and but by then you've practiced this and you'll have that. Now if you think about what a calcium channel blocker is going to do here. So, remember, I guess I'm going to keep emphasizing this, and then we're going to go back to to epinephrine then. When we're doing these blockers, the beta blockers, calcium channel blockers, alpha blockers, we are not killing the person. Okay? It means it's going to inhibit the process somehow. Okay, whatever's going on, it's inhibiting it. We're dosing it up. Maybe you can kill the person, but we're trying not to. So you don't want to, like if you look at this, if you use a calcium channel blocker, what is that effectively? What is it affecting? Depolarization. Does that mean we're never going to depolarize and we're dead? Okay. Does it mean we're not going to depolarize as often? Yes. Okay. If you go back when you talk about acetylcholine, what does acetylcholine do to heart rates? Speed up or slow it down? Slows it down. When you look at that slide, it actually says how it does it. It actually, one of the ways it does it is decreases calcium coming in. That slows down heart rate. So a calcium channel blocker, by affecting this, you basically, it's going to slow down heart rate. If it slows down heart rate, what do you slow down? And therefore, looks like calcium channel blocker is going to be a blood pressure medication, okay? Okay? It's going to affect a lot of things, and that's what I'm going to have you play with. But that's what you need to do for these tests, okay? This is a hard test, but you guys are just getting smarter by the minute, too. So I'm having a hard time keeping up. I think you're getting smarter than my test. That's the way it goes, yeah.
The low blood pressure, when you have the goal of increasing the blood pressure, does it go through all 5 of those in order to increase it? It's not just one.
No,
pathway?
no, because the one pathway is this. We've increased sympathetic and decreased para, and that's because they innervate all these places. That's why it affects everything. Yeah, it's a chain reaction, right? Because that's how our body likes to work, even with the nervous system and what we're going to add, the endocrine system. So all these things are happening simultaneously. But you look at those extra questions. If we use a beta blocker, we're going to only block one part of this, and we're going to see the other one part is going to overcompensate, and that's going to be the key.
So if you wanted to raise blood pressure, would you do the opposite?
Yeah.
You would increase the parasympathetic?
If the goal, which won't be your essay question, but I can have parts of it in. If you had high blood pressure and your goal was to lower it, these arrows switch. Everything stays the same except all the arrows switch, and vasoconstriction becomes vasodilation. It's the exact same response because your baroreceptors. In fact, we'll even do this in lab tonight. The lab will be abbreviated. Okay, I want to just get a basic point out. You're going to do EKGs, and part of it is measuring that your EKG during inhalation and exhalation. So you can measure your heart rate. That's going to change because your blood, believe it or not, your blood pressure changes just by when you inhale and exhale, and this response is automatically making compensation. And we're not going to measure all these other things, but we can actually measure heart rate, and you'll actually see, and this usually works, so we'll put all the data on the everybody's data, that you actually see a difference in heart rate from breathing in and breathing out. A lot of it is because this response isn't just waiting for something bad to happen, like oops, this is tonic. It's simply, this is happening, we're tweaking these up and down constantly, okay, to try to keep sort of a balance here. You ready for some epinephrine? Is that question or just?
Yeah, I was just wondering, the first one is inhibiting the inhibitor, right?
Yeah, that's why that's that inhibitor. But you see, after doing the nervous system, it's like, yeah, inhibiting the inhibitor versus, the first day. So you guys are just like getting a little too smart for me, but I'll try to keep up. Okay, we add the next thing that we added. This is very important. This coordinates the endocrine and the nervous system together. Okay? Usually when I come here, I'm like tired, and then I get excited. Okay? It's like I'm like sleeping in the car, and all of a sudden now it's like, oh yeah, this is cool. I forgot. Okay, so the idea with the endocrine system here is we're looking at a compound related to norepi, which is epinephrine. And the cool thing about it is it has some of the same effects, but it has some different ones, but they work together. And so you want to think fight or flight, in which you're going to basically run away from the bear, or exercising and thinks you're running away from a bear. And the idea overall is this: we want what? Okay, we have all this blood here. We don't want it here, right? We want to increase cardiac output, right? We need blood. We don't want it sitting here. But do we want to blow blood pressure out the roof? No. So we want to increase this, but we want to direct it. We don't want these things to hang tight, but we don't want it to just to go everywhere equally. So that's how they work together. It's like totally cool. So here's our summary chart, which simplifies it a bit, but it's the way we go. So we have this idea of 3 types of receptors now. In the next section, this will come in. So we have beta 1. We'll put alpha. Again, this is another one. It's not the essay question, but you probably write this chart so you remember. And then we'll go to the next thing we haven't covered, the next 2 things we haven't covered in this chapter. Probably stop that. Okay, so those are the different receptors, and now we're doing the difference between norepi and epi. Let's put E for epinephrine, and see how those are related. So again, the beta 1 receptors are where? Where do they locate? Yeah, SA node and ventricular muscle. And when norepi binds to them, it basically does this, right? And again, we don't have to worry about blood pressure. We don't even know well, but it increases, increases heart rate, stroke volume, cardiac output, right? Now, whether it increases blood pressure depends on other things, but that when norepi binds to it, it definitely does that. It increases heart rate, stroke volume, cardiac output. Okay? Epi, the same. So epinephrine is going to help out. We need cardiac output. It says, I'm going to do my part. I'm going to stimulate these things and do the same thing as you, and we'll work together to increase blood coming into the system. All right. When norepi binds to the alpha receptors, and where are they located? On most veins and arterioles. Okay, when norepi binds to them, they're going to cause vasoconstriction, like we just said. If you weren't sure, you would go back to your page and you're like, yeah, I wrote that. It causes vasoconstriction so that we don't just, blood that comes in doesn't just flow like out, leaks to everywhere, right? Because we want to direct the blood. So it vasoconstricts to sort of keep blood pressure up. Now, epinephrine says you got that under control. Okay? I'm not going to do much work there. And again, whether on my notes, because the books, it's like it has some effect. I mean, it's not like it has zero effect. Okay, life is not quite black and white as we want it. It has some minor effect, but then people on the test are like, well, is it none or minor? And it's like, we're saying for our purposes, basically it has no effect. Okay, everyone have that. Okay, so epinephrine isn't going to have any effect on the alpha receptors on the veins and arteries. That's being taken care of here. Beta 2 receptors. Norepi says, I'm busy now, I've done enough, okay? Epinephrine is going to bind to the beta 2 receptors that are located on certain arterioles, such as the blood vessels, the coronary vessels going to the heart. Where else do we need? Wherever you think we need blood directed to on this fight or flight, that's where it's going to go. Skeletal muscle. And the third, that's the brain, a few other things, but skeletal muscle and the liver, because it has sugar stored there that we need to use. And we'll find out a couple other places that we have beta 2 receptors later. So heart, skeletal muscle, and liver. And when epi binds to those guys, it's going to cause vasodilation, because we're going to direct the blood now. So both of them work together to increase cardiac output. Norepi says, I'm going to keep all these under wraps here. And epi says, okay, I'm going to just direct the blood to specific places. And so I'm going to dilate those areas. Now we've increased cardiac output, but we've increased the direction of flow. So overall, blood pressure might increase some, but it might not increase as much as you might think. Cardiac output's going to increase quite a bit. Okay? That's how these work together. So these were the two guys at top the first day, the two systems that control all the other systems. Now you're starting to see the details of that, how they're working together to control our flow of blood, depending upon the needs, depending on our blood pressure needs and our what our cardiac output needs, what we actually have to do. I take my drink of vitamin water. Yeah.
So is epinephrine more of the endocrine system?
It is the endocrine system. So by definition, epinephrine is being released, if I didn't say that before, I probably have it there, by the adrenal gland into the blood. So it's just that they're working together. This is a hormone, okay? It's not a neurotransmitter, but I keep saying compound, but it's, because I can't think of the word I'm really looking for. But it's basically a substance related to norepi that has some similar effects and some different. But it is a hormone. That is the endocrine system. This is the endocrine system and the nervous system working together to achieve a common goal. And you can see they have a commonality to it, and they have their differences, which allow them to do what we want. They allow us to get blood up to our system, increase cardiac output, and direct the blood. Very, very cool. Okay. So, now the two basic things we didn't cover in the chapter. And that will give us enough thought to play with here. And again, from your handout and stuff, I skipped these because, and I'll come back on this, because now we're going to talk about local control. Okay? Local control. So I'm going to put local control over here. Local control of blood into tissues. And I'm going to draw, to kind of draw this, I'm going to draw an arterial. Okay, so this is a specific arterial, or specific set going into a type of tissue, whatever it is. Maybe this is to a particular skeletal muscle or something else. Okay, and I'm going to draw another one because we have two of these mechanisms. Okay, so this is again, capillaries going into tissues. Okay, capillaries going into tissues. This is where the blood is going. Okay, this was like the general way. All of the arterial is kind of going out, but now we're looking at specific ones, and we're going to have local control. And I like to summarize the two that we do here in the sense that for local control, these arterioles are responding to factors locally, and their job is to serve and protect. And we're good.
Whose job is it?
These arterioles.
Oh.
Again, remember how I describe things. I describe things in a way that we're gonna, that helps me, understand. Obviously, they're not given a job description, but in a way they are. Okay, and we're gonna see how they work. These arterioles, they want to basically serve the needs of the tissue, and they're going to constrict and dilate to do that, and they want to protect the tissue from damage, and they're going to do that as well. Okay, so here are the two local controls. The one of them is the first one up here. And we're going to call that myogenic autoregulation. Or here, yeah, this is auto this time. We're going to revisit this in the kidney. Myogenic. And what this is the following. that if you have an increase in blood pressure coming in here, it's going to do one of two things. It's going to dilate or constrict. So, how many people think it's going to dilate? How many people think it's going to constrict? How many people are like, well, let's look at this a little bit closer. Okay. What it's going to do locally is actually constrict. Okay. It's not going to, if you just dilate it, okay, we said, oh, increased blood pressure, let's go, boom. We're not really controlling the flow into that tissue. We want to control blood flow at a local level. We don't want, if blood pressure increases, just to boom it through here. And so you're going to have basically, in response to the stretching of increased blood flow, it's going to constrict, basically cause constriction, a natural thing that smooth muscles do. And what does that remind you of? Stretching coming back, stretching coming back. Cardiac. To me, it reminds me of more in, more out. Right? Why did EDV increase stroke volume? As you put more volume in, it stretched the cardiac cells, more calcium came in, it came back. Smooth muscle works the same way here. When you stretch them, more calcium comes in, because they have that same mechanism, and more will contract, and will basically contract. That's why it's called myogenic for smooth muscle autoregulation. That's how all smooth muscles will work. If you stretch them, it causes, again, because they rely on extracellular calcium, as when you read the end of chapter 12, they basically will respond by the same way that the cardiac cells do, by contracting more. And so increase in blood pressure is actually going to cause them to contract to control blood flow into the tissue. That's why myogenic autoregulation, to be, for my analogy, or whatever you want to call it, for serve and protect, is the protection. We want to control blood flow into the tissue at a local level. So increased blood pressure here will actually not cause it to dilate and increase blood flow into your tissue. It locally is going to constrict to regulate blood flow. So I do this after this, because you're like, increased blood pressure, we're going to vasodilate. Well, we're going to have systemic control over things, but we have local controls too. Okay, and this is the local control. It has to do specifically with the nature of smooth muscles and the idea of that we want to control blood flow. So increase in blood pressure, we're not going to basically throw that out here. Maybe eventually these things will cause an increase or decrease. We don't care. Local control. Increase in blood pressure causes this thing to constrict so that we don't increase the flow into the tissue. We're controlling it.
Is that the tissue that's doing the regulation, or is it like...
This one is the actual blood vessel, the smooth muscles within the arterioles themselves, because that's how smooth muscle works. So it happens to be that it has to do exactly with, that's why it's autoregulation, how smooth muscles work. So smooth muscles, when you stretch them, automatically will cause them to constrict. And so in this case, that's how your digestive system will work too, why that's going to stimulate that, by the way. So that particular one, that's why we're going to serve it for the tissue here. Here it's responding locally, though, to an increase in blood pressure into those arteries that contain the smooth muscle, and that's going to cause them to come back.
Is that specific to every kind of tissue that might be different in the body?
That has smooth muscle?
Yeah.
And in fact, I mean, I guess I hate to say every, because I'm always going to be like burned by that. But yeah, I mean, most the tissues that have smooth muscle, because again, it's not like something we feel like doing now. It's because that's how smooth muscles work. They're going to use extracellular calcium, and just like cardiac, the more calcium, the stronger the contraction. And by stretching, calcium comes in. So that's just how they work. So all smooth muscles work that way. We're dealing just with the ones in vessels. When we get to, what's coming soon? Kidney. Okay? The blood vessels going into the nephrons, the set of capillaries are what? The glomerulus. Okay? If we increase blood pressure, do we want that to flow through just into the kidney, or do we want to control that? We're going to be big doing the same thing, controlling blood flow, that of getting what's going to be filtered in by the same idea, like by having this constriction that coming in. So this is like a basic principle. So that's called myogenic autoregulation, local control. An increase in blood flow will cause these to constrict, to control blood flow. This is how, for my serve and protect analogy, it is protecting.
All right.
Are you ready to serve? Yeah, well, hang on. I'm sorry, say it again? Yeah. So because, again, we kind of went that way. By causing vasoconstriction, that increases resistance, like from the beginning, right? And that will control flow. All right. To get this next thing, and it's pretty important that we get this basic concept of gas exchange. So what we're going to do for this idea of serving the needs, we're going to talk about the needs of the tissues as far as metabolism. And so as far as metabolism goes, like how active are they? How metabolically active are these cells in this tissue at the moment? And the thing there's a few things that relate to that, because basically how metabolically active they are, they're going to be giving factors to tell these arterioles what to do. But one of the main things are understanding sort of cellular respiration, gas exchange within a cell. Because what we're going to do after this test, we're going to talk about gas exchange in general. And when we're doing gas exchange, overall, before we get to that, just the respiratory system, we breathe in what? Oxygen. We breathe out CO2. Well, at a cellular level, when tissues are active, that's what they're doing too. That's why we have a respiratory system. So you're going to take food, and you don't have to, where is this? C6H12O6. That's like glucose. Plus we're breathing in oxygen. We're going to basically use this whole pathway, which we're not memorizing now, and we're going to produce CO2. You don't have to memorize this. Water plus ATP, all this energy that we need to do things. For our purposes, we're only concentrating on that, oxygen and CO2. Okay, the gases that are here. Other things are also going to affect this, but the thing is, if you're highly metabolically active, this is going on quite a bit. So in a highly metabolically active cell, if you're asking the question of relative levels of these gases, if you have high metabolism, okay, compared to other tissues, what are the levels of these gases going to be? One's up, one's down. Oxygen, is that going to be, you're going to have a lot of oxygen in that tissue, or are you going to have a lower amount based upon what's happening here?
A lot of oxygen. A lower amount?
Lower amount. Because you're doing this. In other words, if you're metabolically active, you're doing this. And right now we haven't delivered any, right? We have just what we have. Oxygen is being used up and we are making CO2. Oxygen is being used up and making CO2. So highly metabolic cells, which are tissues, will not have as much O2 because we're converting it, and it's going to start building up that nasty CO2, and CO2 means acid to us, right? And that could be all kinds of problems. Okay, so that's why get this concept. It's going to help you for respiration coming up next too. So as far as metabolically active, the more metabolically the tissue active it is, these gases are going to kind of go that direction. We're going to start using up the oxygen in the tissue and start building up CO2. And that doesn't seem good, does it? Okay, now we have this arterial. And this arterial, remember, came from the left side of the heart, nice oxygenated blood. And so what is it carrying? It's carrying oxygen. And so we want to serve the needs of the tissue. So if you're highly metabolically active, and you don't have as much oxygen, and have a lot of CO2 and other things going on, it's going to communicate through what we're going to call paracrine signaling, which is local signaling. So basically, the oxygen, CO2, and other factors can actually diffuse to these smooth muscle cells of the arterioles. The bottom line is, what are these going to do? They're either, in response to the high metabolism in these gases, these either going to dilate or they're going to constrict.
Dilate.
Because their job is to
Move oxygen to the tissue.
and also it will also then eventually move CO2 out, right? If we increase flow to the tissue, we're going to deliver the oxygen and get rid of that CO2. We are going to serve the needs of the tissue. If you have a tissue which isn't very metabolically active, do we want to dilate there and waste our oxygenated blood? No. That's the idea of locally, we're going to respond to the needs of the tissue, to the metabolic activity of the tissues. So they're going to release factors, and in the book they've got all kinds of other factors. I just want us to concentrate on the gases that you start to get that if you're highly metabolically active, you're using up its oxygen, you're building up CO2, you want to increase blood flow to deliver more oxygen and get rid of CO2. This actually happens locally. And we call this one active hyperemia. A specific...
It's
not paracrine regulation?
It's paracrine regulation is the overall idea, but this particular one, so they both apply. This particular one, which is responding sort of to the needs of the tissue, okay, tissue metabolism specifically, is active hyperemia. And I'm not going to talk about the other one when you have blockages and stuff like that. And again, that's the idea of my serve analogy, okay? Because we want to serve the needs of the tissue. You know, the tissue, these arterioles' job is to provide oxygen, you know, to these tissues. If they need more, we're going to dilate to actually provide more and also get rid of the CO2. You know, I mean, again, in reality, the system is just set up this way, that these factors that are being released by these highly metabolic tissues literally are coming in and binding to receptors on the arterioles, causing them to dilate.
Is hyperemia and hypoemia, is that like vasodilation and vasoconstriction?
I don't know. I mean, I don't know I don't know that word. I haven't even looked for hyperemia. Have you heard that, or are you just coming up with
I saw hyper and I thought more of
yeah.
hyperemia
It's
vasodilation.
yeah, maybe. I mean, I'm like, that makes sense too. I just haven't heard that term, but it makes sense. Did we get that? And this is why I think in the book they put this first, and I'm like, no, I don't want to put this first, because I want you to understand the global systemic level, and then we look at this local control, okay? And that's because it already gets confusing, because most people would go, increased blood pressure, we're going to vasodilate and cause, you know, to lower, but locally we're not going to do that. You know, systemically we'll take care of what we need to do, but locally their job is like, hey, you know, I'm in control of here. I might have a boss tell me what to do somewhere else, but you know, other hormones or neurotransmitters. But locally, I'm going to respond to just, you know, local blood pressure conditions and local tissue conditions. So we have, and again, if you go back to the very beginning when we're doing the global idea of signaling throughout the body physiology, we have, you know, systemic signals and we have local signals, and they're all trying to achieve homeostasis. Here's our systemic system working. That's why this is a beautiful board right now. And here is our local system working in the circulatory system. Now, this is just great stuff, okay? It's like you've been waiting. We should have just started with this, because you wouldn't, without the nervous system, this stuff would have been like impossible. Now it's like very manageable, I think, for most of you people, because you guys are just that much smarter. So we're almost peaking. Cardiovascular, kidney, and then, you know, Thanksgiving, final test, we're out. Okay, so, you know, 2 weeks from today is our final, I think. So we're our 2 months. Sorry. You can see where my mind is too. Or unless you just want to do that, we can pretend. Okay, we just get it done in 2 weeks. We'll put up like these fake people figures in case someone comes walking by. You know. Any questions about this? So we're down to the last thing. And this I don't think is an updated handout, but it's in your PowerPoint. So, and I don't know if I showed this or not. This is like a minor thing. Let me just show this. When we're talking, you know, we talked vasoconstriction, vasodilation. But we've been talking, you know, just instead of looking like the heart, in which we've got sympathetic, para, both on, we're only using sympathetic. So how can you constrict and dilate? Well, the idea is that you have sort of a natural tonic level, okay, of sympathetic, of norepinephrine being on the alpha receptors, and that's creating some vessel length. So if you want to vasoconstrict, you increase that. But if you want to vasodilate, you simply decrease that level. And that's how one neurotransmitter can basically end up causing constriction or dilation, because you need something. You're starting with something in the middle. So maybe that's obvious, but you know, it's good to kind of look at that. So we did the hormonal. We are not going to be tested on this meta-arterioles, so you can sort of skip it. It's another way to sort of control where blood flows, but I don't feel like telling you about it. You can read it for fun. There's fun. Wow, that was cool. Okay, this is not as much fun. This is what probably is not in your handout. In your handout, we're finishing up with capillaries. And your handout talks about, after this, we'll talk about fenestrated and continuous capillaries, okay? But that was just too easy for us. I had to get to this because we get to talk about osmotic pressure. Okay, and that's the last thing. Are we still good on that 20 years? Are we getting okay. All right, so I want to erase this. I'm going to use it over here. So we're talking about blood flow now into the capillary. Remember, the capillaries basically are very, they're exchange epithelium. We don't have smooth muscle, all this stuff. They're supposed to exchange material from the blood into the interstitial fluid to the cells and back and forth. But we're going to be talking about now where fluid is going to go. And if we remember from, I keep saying, you remember because you remember everything, right? We talked about, and I'll erase this in a minute, but we were just doing fluid compartments. We had sort of the intercellular compartment. Remember, 2/3 of the water, you just did this, was actually in it. And then we had the extracellular. Right? And that's 1/3. And but the extracellular was divided into two parts. We had the plasma, and then the interstitial. And we probably have mentioned at some point that, hey, it's important to have the right balance of this. Okay? You didn't want to have, of this extracellular, having too much in the interstitial fluid probably wouldn't be good. Having too much in the plasma probably wouldn't be good. We need the right balance. And what's sort of cool is, when blood is flowing through the capillaries, we actually have sort of some fluid exchange going on between these compartments. And so, let me just kind of show this. Don't worry about the numbers. Sometimes numbers help people get it, but you don't need to know the numbers. What I want us to follow here is the following, and I'll kind of put it up here too. All the words, by the way, are on these PowerPoint slides that, in case you print them out or you look at them, but not on the handout. So we have two ends here. We got blood coming in from the arterioles, and we've got our capillaries and exchange, and then we have our venous side of things. Now, the idea of the fluid exchange, and here is again the plasma, and here is the interstitial fluid, is we've got two forces controlling fluid movement between these compartments. We have blood pressure, okay, which we actually call hydrostatic pressure, because it's in the vessel itself. We're not looking at global blood pressure, but it's the pressure within that vessel, okay, at the arterial end. And that's because the connections between the cells are what they call leaky, right? That that's going to be pushing fluid into the interstitial. But we have an opposing force, and that opposing force is within these vessels. So if we just draw my idea of this, or my picture of it, okay, so here's the arterial end, here's the venous, okay, and here's blood coming in, and again, blood pressure, or hydrostatic pressure, we'll put BP for now, is driving blood into the interstitial. But the serum, I just go to plasma, the non-cellular part of blood isn't just water, it's got a bunch of stuff dissolved. Something it has involved, a lot of things it has are these plasma proteins that I'll actually mention next Monday on chapter 16 a little bit. And they include things like albumin, clotting factors, antibodies for some. But a lot of these plasma proteins, by the way, are made by the liver. Liver is very important for making, especially albumin, which is really important, clotting factors, and we'll talk about blood clotting a little bit. So those proteins are there. Okay, those proteins aren't in the interstitial fluid. All right, so remember the way water is, right? Okay, water is looking down, and it's seeing what there?
Plasma.
It sees plasma, but it's seeing what? Proteins. To it, it says protein party. Okay, so just like ions, basically, which couldn't cross, attract water by what we call osmotic pressure, right? And we were making easy for us, water goes to the party, but it's being attracted. That salts create an osmotic pressure that draws water to it from that compartment. Okay, this is doing it as well. We call this colloid because we're dealing with protein now. Colloid osmotic pressure means these proteins are drawing the water back. It's creating pressure drawing water back. Having proteins in your blood basically helps keep the water out of your interstitial fluid and keeps it back, in the blood where it contained. Blood pressure right here is pushing it out, but colloid osmotic pressure is sort of bringing it back. Okay, these are the opposing forces, right? That's forcing this way. This is forcing this way. Okay, so that's why when I'm big on osmosis, you're just going to see, yeah, that's how we do things. Okay, so that's colloid osmotic pressure. Those are the two forces. Right, I have that there. Blood pressure pushing it out, and we have this colloid osmotic pressure pushing it this way. Okay, does everyone get those two forces?
Blood pressure is pushing what out?
Pushing fluid,
Oh.
out from the blood into the interstitial fluid. It's pushing from, like when we did it this way, it's pushing, H2O and whatever's dissolved from the plasma into the interstitial fluid.
But the colon
The colloid is opposing that, okay? It's trying to keep it there. Blood pressure is pushing it out, but the proteins are trying to draw it back. And those are the two forces. Now the key is, on the arterial side, blood pressure is higher. Okay, because remember, arterial side, blood pressure is higher. And if you kind of look at the numbers without memorizing them, you can see that on this side, blood pressure basically outweighs osmotic pressure. Has a greater amount, there's a greater pressure. So there's a net flow of water on the arterial side into the interstitial fluid. Okay? On this side, basically, there is actually still a net flow of the water and whatever dissolved, of the plasma into the interstitial fluid. Now, I have these words written on separate slides, but I'm just saying them all now. On this side, okay, when you go through the capillaries and everything, what happens to your blood pressure? Is it the same?
It drops.
It drops. So you look on this side, the osmotic pressure stays the same. But now on this pressure, instead of being 32 on this side, it's only 15 on this side. This stayed the same. That means on this side, osmotic pressure draws it back. So that overall, there is no really net water movement between the compartments, but there is movement on this side basically of the plasma, moving in, and then the plasma moving back. And this is the balance that we want. Okay? And we're gonna mess it up in a minute because we're gonna be out of homeostasis. This is the basic idea of flow within this capillaries. Basically you'll have fluid on the arterial side go into the interstitial fluid, and then it will be returned on the venous side because blood pressure is dropped, but the proteins definitely win in that case and draw it back.
Draw back the water?
Draw back the water and everything that's out of it. I mean the plasma. So it's the water and ions, things which are dissolved within it. And we'll show you everything dissolved in the plasma. But for us, somewhat, the water component. Okay? Does that sort of start to make sense? And then we'll mess it up and see if it makes sense. Again, all the words are there, and you can kind of see this. Again, I define the two pressures, hydrostatic pressure, osmotic pressure. And I say that the reason, by the way, if we had more pressure here, then this wouldn't work. But this pressure is greater, and so fluid is going to enter this interstitial compartment. So define colloid, get pretty much what I'm saying here. So we get, on this side, osmotic pressure is winning. On this side, the blood pressure is winning. That's why there's a net flow. On this side, the osmotic pressure is winning and pushing it back. Now, by the way, again, I have that. For people, because there's always a couple out there, okay, and you know who you are, and they're actually looking at this intently and actually seeing something here in which you put 10 in and you only got 7 back, Mike. Wait a minute, that doesn't seem right. So to be honest, the idea is there is a little water that stays in, and it gets returned through the lymphatic system, which we're not going to go too much into. Lymphatic system, contains antibodies and those type of cells that will be basically put into the circulatory system. That's how that is returned to us. But so that's just like, because someone's going to ask that. That's not on the test. But you can see there's a little difference here. But the whole idea, the basic point is, under normal conditions, we have this, because of these two pressures, we have this flow. On the arterial side of the capillary, we have basically a net fluid gain into the interstitial fluid, from the plasma, and then it gets returned on the venous side. Guess what's coming? Liver failure. Let's see what happens. Okay? Okay, so liver failure, it's going to affect specifically, I don't even get to that, but what is it, what at least, well, kind of we're getting to it. What of this whole thing is it affecting? If you're having liver failure,
Glucose levels.
well, let's see, no, I want to get more specific on this. It's we're doing with the proteins now, okay? Yeah, it's going to cause all, liver failure is bad, okay? We can spend a long time on that, but right now we're talking just about this, and it's basically going to cause too many proteins or not enough. Not enough. And we call that, we'll put something on it, hypoproteinemia. Not enough proteins, okay? Because we're having, the liver not working as well. Okay. So, now let's see what it's going to affect here. Okay, so we just determined liver failure, right, in this particular set of circumstances, we're looking at its inability to make these plasma proteins. And so the next thing is to think, okay, well, what is that affecting? What pressure is that affecting?
Osmotic.
And what's it doing to it? Increasing or decreasing?
Decreasing.
Okay, less, not much of a party. Okay, so it decreases colloid osmotic pressure. Okay, does everyone see that? Liver failure, again, by definition of what I'm saying here, it normally produces these proteins. We're not producing as much, so we're not having as much pressure drawing the water, keeping the water in. And therefore, what's going to happen? We have an increase, if you lower colloid pressure, we have an increase of water that stays in the interstitial fluid. Because what draws it back, hey, it's not as much. Simply not worth coming back to that party. So an increase in interstitial fluid volume. And we actually have a name for that too, which is what? If you have fluid buildup in your tissue. Edema. You also, what will be happening to your general blood pressure? If you got two compartments. You've got your blood interstitial fluid. If you have an abnormal excess amount of this extracellular, if it's going into interstitial fluid, it's edema. What's it doing to your blood pressure then? Lowers blood pressure. See, we're not doing some reaction to that. We're talking about immediately what's happening is if you only have this much water out here and you're putting it in there, there's less in here. And so it actually, you're going to have a lower blood pressure. Again, we won't go beyond what's happening yet from that. So if you're putting more here, what you're doing, you have less left here, and so you actually can have sort of a lower BP as well. The primary effect we're looking at is this though. Liver failure, you start having, you're not enough proteins here, you're hypoproteinemia. Therefore, when you're doing this game here, fluid is staying in the interstitial. It's not able to return, and you're getting this buildup edema, and you're lowering your blood pressure. Again, I don't know how many people, sort of dealt with people with edema. Now, how many years? My mom died maybe 4 or 5 years ago from cancer. One of the reasons I'm interested in cancer. It had metastasized to her liver, and when metastasis, which is 95% of cancer death, the cancer takes over whatever organ it's in. So, if you have mets to the liver, it basically means it's going to be growing and liver function is going to start failing. And so, it took months, but the last few months, the idea is her arms were so swollen because of edema, because water would, fluid was, because of the lack of liver proteins, water is just building up where you couldn't even move her arms. And for some reason, and when you're in healthcare, you tell me this, okay, 21st century, what they would do is put these wraps on and try to squeeze the blood back, try to actually kind of increase the pressure here to squeeze it back. That still seems like archaic. I don't understand why you can't just add something that acts like proteins, but that's literally what we would do. And they would give diuretics, which doesn't make any sense too, because your blood pressure is already low. If you give a diuretic, which makes you lose volume, you're going to lose volume here. And so I was actually, a nurse came over and she stood up and took her blood pressure, and it was like so low. I'm like, this is nuts, okay? I don't understand how, okay, or the way it is. But the bottom line is, when I was doing this, it sort of hit me of why, why you would develop edema. And it's not the only way, cancer's not the only way you develop edema. But the whole idea is, one of the main things is the idea of liver malfunction, which obviously affects everything, like you talk about glucose. But in this case, it's affecting fluid balance in these extracellular compartments. So without liver, you're not making these proteins. Probably not going to be able to clot very well either. You're not making these proteins. Water's building up interstitial, and that is edema. And you can play the opposite game with hyperproteinemia as well. That's kind of what I want you to be doing. Some of the extra questions involve like that. Does that make sense? Okay. Last couple slides, which aren't as hard. You guys are good. You have this. Again, I asked that. So here's what you have on your handout. It's just like so easy for you guys. I just want to show it. Really, and the main thing is this. When you're looking at, we don't want the same fluid flow into tissues the same everywhere in the body. And we actually, the ones which, and we'll show a picture, here's again what we're calling leaky in general, but I don't like that word. Most tissues, I just kind of put over, most tissues are continuous, like that you have some of this, like we're talking about, some fluid flow relatively easy between tissues. Fine. That's just called continuous. That's most cells. There's some places in which you need high volume exchange, where exchanging just between cells is not enough. You actually need pores, okay? And so if you look at these, they're called fenestrations or pores. This will allow high flow, flow through of fluid, okay? Where do we need that? Kidneys and intestines. Remember, I've been saying this a lot. We have 180 liters a day going through your kidneys. And that's 180 liters a day. That's 180 if you can't understand my accent. My St. Louis accent. Although Cardinals lost today, Dodgers are getting closer. We have to. And so 180 liters a day, is a lot. We only have 3 liters of blood. That means 60 times a day our blood going in. So those are going to have fenestrated capillaries. The glomerular ones we'll talk about will have fenestrated. Same thing with the intestines. We're going to see it in our last unit. We put in like 9 liters a day. I think it's 9. It's at least 9 into our digestive tract. We got saliva that's spitting out of me all the time, and it goes to my digestive tract. All the hydrochloric acid. Well, obviously, do we want that to stay continuing on out, or do we want it to come back into our body? I choose to come back in the body. Okay. Otherwise, it's really a sad day on the toilet. Okay. You can literally, and that's why it's so dangerous. Like when you think about this too, you think about how, like for an infant, diarrhea is deadly. Because if you don't reabsorb that water, you only have 3 liters of water. I mean, death could be almost immediate. That's why it's really not funny at all in that sense. But I'm not laughing. The key with this is the intestinal cells have to be able to reabsorb vast amounts of water too, so there's fenestrated capillaries there. So out of all that, that's the main point here that I want. Most cells have continuous, but for high fluid exchange like these guys, you will have fenestrated. Okay? Atherosclerosis won't be tested. It's interesting, but I got you covered here for this test, okay? So, it will not be. I have it up here. It's cool. You can learn it, but it's not going to be on the test. So but you can look at it for fun. But I don't want to cover it because I have enough. Chapter 16, you'll look at. It's going to be almost 5 note cards type of order. I mean, it's not going to be that much material. So it would take 30, 40 minutes at the most on Monday, and then it's really that's the last of the material on the test. I mean, that's the last new material on the test. That means you will have the rest of the time to do is to start looking at those questions. You should start looking at them already, reviewing certain things, and definitely Wednesday should be extra questions, all reviewing. Make sure you get those. You really want to look at those pretty carefully, even over the weekend. See if you start getting them. There's some material in there. I talk about hypovolemic shock. I'm not going to talk about hypovolemic shock here, but and you don't know what it is. Where's your phone, okay? You can literally look it up. But we're going to look at some of the symptoms of it, and it's going to make sense based upon this, and you'll see those questions. So, and guess who will we revisit too? Drugs, okay? We're going to revisit drugs and show how it specifically affects blood flow and different things like that as well. So we get cocaine involved again. It's not dead yet. So you look at one of those questions on there too. The cocaine and nicotine, we're revisiting them. So, okay. So lab itself, by the way, I'm going to make it pretty abbreviated. We're going to do EKGs. We're just going to measure heart rate for breathing and basically after exercise. Okay? So that'll be available. Again, I have plenty of time tonight. The lab will be over probably by 8. I'm there 2 more hours if you want to talk more about it. Let's go over this, look at your test, anything you want to do is up to you. Hi.
So I was on a couple of weeks and I was I emailed you about it, and when would I get to
When do you want to take it?
I might not be able to take it or weekends.
What? Is that
I might not be able to take it until next week or the weekend, because the only days I have off are Saturdays.
Very hard.